Good afternoon, everyone. This is Celso Batalha, Cha10, and today, in fact, this week we are focusing on the sun. So this chapter has probably it has two main subjects, and the first one, it describes what's going on inside the sun. And the second aspect is what goes outside. Okay, so let's see how that goes. As far as what's going on inside the sun has three main regions. It has the core, has a shell where radiation moves outward, and has another shell where a motion of rising hot gas takes place, and this physical process is called convection. So again, the interior part of the sun has the core, has the radiative shell where diffusion of radiation takes place, and has a third shell where convection takes place. So hydrostatic equilibrium, this name here, is important because it establishes a perfect balance between two forces, two competing forces, here represented in this slide by the blue arrow. These two competing forces are the inward gravity force, which is the weight of the star above that point, and the outward force is produced by gas pressure, acting as if a bunch of little particles, ions in fact, were trying to expand, trying to pull that shell outward, and the balance of these two forces are perfect at any given position. For instance, here on this region in the convection zone, at the base of convection zone, gravity and the outward force caused by pressure, they balance out, and their intensity are less than it is in the radiative shell, and they are even less if you compare that with a region closer to the core. So again, three regions in the solar interior. Now, in the core of the sun, what's the important part of that part, of the region, that part of the sun, that sector, is the onset of fusion. So fusion reactions take place in the solar core, right there, and as a result of these fusion reactions where four atoms of hydrogen are being fused into one atom of helium, energy is being produced. Gamma rays comes out, and here it's being shown this way. So you have four protons, 1, 2, 3, 4. So protons, which are the nucleus of hydrogen, they fuse, and the fusion final product is one atom of helium plus energy plus neutrinos. So neutrinos right here. So neutrinos are particles that once they are created, they interact very little with the surrounding gas, and they escape the core. Whereas radiation, the gamma rays, takes long time, takes millions of years to reach the outer atmosphere. So neutrinos escape right away. Radiation or light takes much longer time to escape the sun. There you go. So why energy is produced? Well, if you take the energy contained in four protons or in four atoms of hydrogen, and compare with the energy that is contained in one atom of helium. Remember, 4 atoms of hydrogen are converted into 1 atom of helium. When you compare those two quantities, there is a difference in energy. There is a difference in mass. And that difference in energy is the one that is pretty much associated with the flow of neutrinos and gamma rays created in the core. Now the gamma rays, this radiation is the one that diffuses itself through the radiative shell and helps to keep the sun balanced in hydrostatic equilibrium. So there are several ways in which fusion can take place, and in the core of the sun there are two main chains or two main reactions. One is the proton-proton chain, and the other one is the carbon, nitrogen, oxygen, the CNO chain, which is more important when stars have somewhat large masses. But this diagram indicates the steps taken or leading from 4 atoms of hydrogen to 1 helium atom. Okay. So the radiative zone again is where radiation moves outward, and eventually in the outer layers convection will take place in the convection zone. So those are the three regions in the solar interior. Now we do not observe the solar interior. In fact, of all the stars, the region we really can have direct observations or direct contact is or are their atmosphere. So the atmosphere is the region from which radiation comes from, and as was pointed out in previous chapters, especially chapter 4, radiation, as it interacts with the atmosphere or with the interstellar gas, radiation imprints information about the physical properties of this gas, and when astronomers capture light, it brings also floating of information about these regions. So again, we do not directly observe the solar interior, but what astronomers found by doing detailed observation, high-resolution observations of the solar atmosphere, they found, especially using Doppler effect, they found the surface of the stars, they pulsate in multi-mode ways. So there are cells that are moving towards the observer and cells that are moving away. So we have red shift and blue shift, and this can only take place if the entire internal region of the sun is undergoing this pulsation or this multi-mode pulsation. So detailed observations using Doppler effect of not only the sun but also stars in general, plus a modeling of how this pulsation takes place in the solar interior, constitute one of the robust tools that astronomers have to model the stellar interior. So helioseismology is pretty much that. It is a tool, but also is a new branch of science. So helioseismology is the study of these pulsations on the solar atmosphere, and then you have astroseismology that also observes and model pulsation that occur in stars other than the sun. And for astroseismology, not only Doppler effect can be used when very broad and deep absorption lines are modeled, but also astronomers can use photometry for that process, for that particular process. And this is called astroseismology. Astroseismology. Okay, so we saw the solar interior consisting of core, radiative shell, and convective zone. So the atmosphere is also divided in three main regions: the photosphere, with a temperature of about 6,000 Kelvin, the chromosphere that lies above the photosphere. The chromosphere is slightly thicker, about 7,000 kilometers, and the photosphere is very thin. In 400 kilometers, which is about 300 miles in thickness, that's where most of the solar radiation comes from. So on top of the photosphere, it lies the chromosphere, which has about 4,000 miles in thickness. And chromosphere is a region in which the temperature rises up from low values of the minimum temperature in the photosphere, about 3,000, 4,000 degrees, and rises up to 10,000 degrees or so. So in the chromosphere, several emission features are formed because of this reversing temperature scale, and astronomers can pick that in observations and also in modeling. So we talk about photosphere, we talk about chromosphere. So let's talk about corona now. Corona is the latest of the three atmospheric regions. See, the corona is kind of a halo. You cannot see it unless the sun is in eclipse, unless the moon is being the sun's photosphere is being eclipsed by the moon photosphere. So corona can reach temperature of 1,000,000 degrees, 2 million degrees. It's a very high temperature, but it's very thin gas. That's why we don't see it. We need to block out the photosphere so that corona can be, the term can be observed. But if you have X-rays detectors, if you have ultraviolet detectors, you can pick up on that radiation. So we studied the three regions in the atmosphere, the three regions in the solar interior. And to close the chapter, you should have an understanding of solar activity. The sun has magnetism, and this magnetism, which is generated by circulation, by ionic or plasmic circulation, and as plasma circulates, it generates magnetic fields. These magnetic field lines can be twisted, can undergo reconnection, and as a result, it creates very strong regions where the concentration of these field lines are very intense. So those are called sunspots. So what I'm showing here is sunspots. Sunspots are regions where the magnetism is so intense that prevents the upward rising of hot gas heating up the photosphere. So that is the sunspot. So the sun goes in activity cycle where the number of spots change from a maximum to a maximum again in a time scale of 11 years. And astronomers found that during the cycle of 11 years, this polarity, the magnetic polarity of the sun switch, so that the north magnetic pole and south magnetic pole, they change location in a very short amount of time, and the sun is indicating a 22 years of magnetic cycle. 22 years of magnetic cycle. So this astro tool is gives you a nice tour on the solar core, and I recommend you to take a look on it. And I'm not going to do it, but follow that one, and it has illustrated quite well the PP chain, the proto-proton chain. Okay, so those are the main points of this chapter 10. and I'm closing up now.